Welcome to today's Explainer. I'm absolutely thrilled you're here because honestly, we're looking at something that's just fundamentally reshaping modern manufacturing. For the longest time, right, laser cutting was kind of viewed as this super high-end niche capability. But if you're in senior management, procurement, or leading a brand today, well, you already know that's just not the case anymore. It's literally a critical industrial requirement now. And we're not just going to sit here and talk about how a machine works on a factory floor. No way. We're going to look at this strictly as a vital business lever. It's the engine that dictates your production speed, your per-part cost, and the ultimate quality of your product. So let's get into future-proofing your production strategy for the year ahead.
Okay, let's dive right into this idea. In 2026, the focus is on AI-driven quoting for transparency and fiber laser efficiency for sustainability. As senior stakeholders, you aren't just out there looking for a shop that cuts metal anymore. That's the old way. Today, you need transparent pricing models driven by artificial intelligence, and you absolutely need highly efficient technologies that actually support your corporate sustainability goals. These are the big-picture, macro-level industry shifts that are going to define your global supply chain strategy this year.
So here's our roadmap for today. We'll be covering the 2026 sourcing landscape, strategic technology choices, optimizing the sourcing workflow, evaluating supplier capabilities, and finally, controlling costs and risks. Quick and to the point, we are covering exactly what you need to navigate all your sourcing options effectively.
Starting us off with Part 1, the 2026 sourcing landscape.
It's wild how specialized the global sourcing market for laser-cut components has become recently. Fundamentally, laser cutting is a non-contact, thermal-based process. It uses a super-focused, high-power beam to literally sever materials. And this brilliantly illustrates why buyers are prioritizing it over traditional mechanical cutting, like, say, CNC milling or die cutting. First off, the precision is just staggering. We're talking standard tolerances of plus or minus 0.1 millimeters. That's tiny. Second, you get minimal waste because advanced nesting software packs those parts incredibly tightly onto a single sheet. But honestly, the absolute biggest deal for your bulk orders? No physical tool wear. A laser never gets dull. This is a massive win for your quality control teams because it guarantees the 10,000th unit is identical to the very first one, all without the setup times you'd usually need for physical tool changes.
Moving on to Section 2, Strategic Technology Choices.
You know, the type of laser sitting on a supplier's factory floor actually directly determines your project's price point and what materials you can even use. In 2026, it almost always comes down to two players, fiber versus CO2. Fiber completely dominates the metal fabrication market right now. They use solid-state diodes transmitted through a fiber optic cable. For you, the buyer, this means significantly faster lead times and lower per-part costs, especially for things like stainless steel and aluminum. On the flip side, CO2 lasers use gas mixtures stimulated by electricity. Now, they might be an older technology, but they remain absolutely essential for organic materials. If you're sourcing custom packaging, textiles, or maybe some slick wooden retail displays, your supplier absolutely must have CO2 capabilities.
Now, what's really interesting about this matrix is how it acts like a perfect decision tool for leadership. Let's break down these operational differences. Look at energy efficiency. Fiber lasers operate at high efficiency, which means lower overhead for the supplier. And hey, those are savings that should be passed right on to you. CO2 lasers, they have lower efficiency, so higher overhead. Then there's maintenance. Fiber lasers have extremely low maintenance because they don't have moving parts or mirrors. CO2 lasers, though, high maintenance, requiring complex mirror alignments. And speed? Oh man, fiber is like 2 to 3 times faster on thin materials, which is a total game changer for high-volume automotive or electronics parts. CO2 really only wins on speed when cutting thick nonmetals. So understanding this matrix means you know exactly what you're paying for on the factory floor.
All right, Section 3, Optimizing the sourcing workflow.
Navigating a contract smoothly requires a rock-solid, structured workflow if you want to avoid hidden costs. And it really all starts with this one technical concept, the kerf. Kerf is basically just the width of the material removed by the laser cut. So why on earth do you need to care about this? Well, because during that critical technical file preparation phase, when you hand over your DXF, DWG, or STEP files, your engineering team has got to account for this kerf. If they miss it, your parts simply won't fit together, and you're going to end up paying for some very expensive scrap metal.
Let's move to and see how this actually builds into our day-to-day workflow. Step 1 is that technical file prep we were just talking about. Step 2 is material selection. The grade of material is a huge deal here. For instance, asking for cleaner laser-grade steel lets the laser cut much faster, saving precious machine time.
Step 3 is nesting and yield optimization, basically how parts get arranged on the sheet. And Step 4, post-processing. This is a big one. The thermal laser process often leaves this burr, sometimes called dross, on the edge of the metal. As a buyer, you've got to make sure your initial quote explicitly includes post-processing stuff like deburring or tapping, or I promise you, you'll be hit with surprise charges later on.
So, I really want to focus on that third step for a second, nesting, with a number you should definitely memorize, 90%. A high-efficiency nest targeting 90% or more material utilization is going to directly lower your per-unit cost. Professional suppliers use advanced software to arrange your parts, kind of like a giant puzzle, on the metal sheet. Every single percentage point of material you save here drops straight to your bottom line. It's a massive driver of efficiency.
Moving right along to Section 4, Evaluating Supplier Capabilities.
It's a tough truth, but not all laser cutting shops are created equal. So here's the golden question for your next supplier audit. Are we matching the hardware to our dimensions to avoid markups? Think about their bed capacity. If you're trying to fit, say, 3-meter-long parts on a standard 1.5 by 3-meter bed, that's just a recipe for costly workarounds. If their hardware doesn't natively match your part's physical dimensions, you are paying unnecessary markups. Simple as that.
Now, beyond the physical bed size, there are a few core metrics that prove a factory's true readiness. First up, machine wattage. A shop running a 12-kilowatt fiber laser is going to cut way thicker plate and do it way faster than one stuck on a standard 3-kilowatt machine. Then, look for automation. The most competitive suppliers are running 24/7 automated loading and unloading systems. This kind of setup drastically reduces lead times for high-volume orders. Third, ISO 9001 certification. That is the absolute bare minimum you should accept, especially in medical or aerospace. And finally, automated optical inspection, or AOI. This is where the supplier uses smart cameras to check part dimensions against the CAD file in real time. That's how you actually guarantee quality at an industrial scale.
And that brings us to our final section, Section 5, Controlling Costs and Risks.
Look, understanding exactly where your money goes allows for far more effective negotiation. So what's driving the cost? The biggest one is machine time. The crucial point here is that complex geometries with lots of pierces or starting points take way longer to cut than just straight lines, which obviously costs more. Then you've got assist gases. If you need a pristine, clean edge, you have to use nitrogen, but nitrogen is significantly pricier than oxygen. You also have to factor in material market price fluctuations, which directly impact how long your quote is even valid for. And finally, setup fees. For really small batches, just loading the program can literally take longer than the actual cutting itself.
But hey, cost is only one side of the coin, right? We've also got to talk about physical risks, specifically the HAZ, or heat-affected zone. Because laser cutting is an inherently thermal process by nature, the intense heat can actually slightly alter the material properties right at the very edge of the cut. It's a potential pitfall you really need to be aware of. And the heat-affected zone is just one piece of the puzzle. You also have to manage material distortion. Honestly, thin sheets of metal can completely warp under the intense heat of the laser, so you really have to check that your suppliers are using cool cutting technologies when they need to. You also need to audit their gas purity. Inconsistent gas purity can cause carbonization on the cut edges, and for brand owners, this is a huge deal. Carbonized edges mean your paint or powder coating is just going to flake off down the line. That leads to disastrous product failures and some incredibly expensive warranty claims. Nobody wants that. So, as we wrap up, I want to leave you with this final, provocative thought as you dial in your 2026 strategies. Is your supply chain actually leveraging AI-driven quoting and fiber laser sustainability to stay fully competitive? The whole industry is shifted. The tools to secure, transparent, predictable pricing and highly sustainable manufacturing are literally sitting right there on the table. Choosing partners who integrate these advanced technologies is absolutely the best way to protect both your final costs and your carbon footprint moving forward. Thanks so much for joining me for this explainer, and here's to building a much leaner, smarter supply chain this year.